Oh, okay.
Hello, everybody, and again, I'm very sorry for inconvenience. This is my PhD dissertation defense session, and I am honored to have you here as my committee members. I really appreciate your time, and I hope I worth the time that you're giving to me. First of all, and before beginning, I want to thank two special persons here in this meeting, Dr. Malki and Dr. Zhu Han. They were very helpful, very kind, and very generous, patient with me. And they honestly, I can say they really tolerated me, and they were very patient with me to just take these steps toward this session and this meeting right now here. I want to thank them, and I really appreciate their help. I hope I can, just return the favor that they're doing to me someday, somewhere. And also I want to thank Dr. Pan for our meetings that we had, internal sessions. He really helped me with his ideas and insightful comments. I really appreciate you, Dr. Pan. You always were like some of those hints that I couldn't consider by myself. Dr. Raja, thank you for giving me the chance. I know that you're very busy and you have a lot of meetings to do. And it's very important for me to have you here as a very important person in committee. And also Dr. Wang, which is who is like the idol in the community in the power system and smart grid, cybersecurity, and I really appreciate him as well to give me the chance to be as a committee member in my PhD defense session. So after this initial and small introduction, I'm going to start the defense session without any further ado. So today I'm going to talk about detecting cyber attacks to smart grids and increasing the resiliency using data-driven algorithms. So I hope that you enjoy my presentation. So the presentation outline is about the introduction to smart grids and cybersecurity. I'm going to briefly talk about the smart grids, electricity markets, and the cybersecurity concepts. Then I'm going to go through three of my main works or contributions during my PhD, and I am going to present what I've done and what would be the cons and pros for each method. And then finally, I'm going to talk about the future work and a conclusion about my dissertation. So we'll start from the introduction. The smart grids are new infrastructure and new technology that's embedded into the power system, and they brought a new they brought novelty and creativity, and they brought a lot of challenges with themselves. So smart grids consist of different parts, I can say. The main part is system operator, the one who's in charge with the security and reliability of the system, the one who is in charge with the frequency and voltage in the system. And the other part is distributed generators. Distributed generators are a new concept of the generation that they have their own challenges. Basically, they are not like the conventional gas or nuclear units. They are mainly consist of the winds, biomass, PV, and those new generation of new generation of the production. The other part are demands, which basically these demands also, they have their own challenges, and they have their novelty, and they have their own infrastructure to deploy. The most important part in the smart grids are the measurement systems, the one that we are going to focus today more on these measurements and these smart meters. Data collection is also another important part of the smart grids, that all of these measurements are going to be collected and sent to the cloud-based server based using these access points. So I can say that the smart grids consist of a lot of different technologies, different infrastructure, software and hardware, from the demand response to the power consumption control. And also I can say that it's all about the controllability and observability of the system, how we can control the system and how we can do it in a very optimal way. Finally, I can say that, well, none of these infrastructures or none of these technologies cannot be used without considering the big data that is involved in the smart grid. So basically, we can divide it into 3 different categories: from the data organization, how we ingest the data, how to our models, to the data analysis, which basically is about forecasting and anomaly detection, customer profiling. We're going to talk about some of these parts here today, and where some of them are people in the community working on. And the last part is the data visualization, which is about how we infer the concepts from the data, how we get the insights out of the data, raw data, how we turn the raw data into information. What about the electricity markets? Electricity markets are also the same, follow the same concepts. Well, we all have those, we still have those different participants in our models. We have the system operator, which, as I said, is who is in charge of the reliability and secure operation of the system. We have the generation units, big generation units and small generation units. Big generation units are the traditional ones, and smaller ones are the generation units that we are going to deal with in smart grids. We have the market management part, which basically is in charge of the transactions, the contracts, these different types of the electricity markets that I'm going to talk about in a couple of slides. And distribution systems, which are actually the ones that compose the smart grids. Smart grids are nothing but small distribution systems that they communicate together and also communicate with some centers. So a smart grid operator, customer, end users, as I say, smart end users, distributed energy resources, as we talked, and load aggregators or retailers that are another part in this game or in this infrastructure into the smart grids. Well, as I mentioned, the smart market management operator is in charge of the electricity markets. Well, there are a lot of those electricity markets. We pay attention to day ahead and real-time market today. And there are a lot of those, different types of the markets, like the auxiliary markets, like the reactive power markets, or bilateral contracts, different version of the contracts. But we're focusing on these 2, day ahead and the real-time market. What is a day ahead market? Day ahead market is nothing but clearing the market based on the predictions of the tomorrow, what happens in tomorrow. So that's why we call it the day ahead. If you just look at the timeline here, if we're going to clear the market for tomorrow, we have to do some transactions today based on the predictions. And the real-time markets are the balancing markets. Well, because we did the previous calculation on previous market based on the predictions, so there would be some errors, and we need to make sure the security of the system is maintained, the frequency is maintained, voltage never collapse in the system. So we have the real-time or balancing market. And well, if I wanted to show the difference in economically, the difference between the day ahead and the real-time electricity prices or markets, I can show the difference between these 2 price or these 2 state variables that I'm showing them here. Well, it's nothing but the real-time electricity market and the day-ahead electricity market, which, as you see, the real-time electricity markets are like the most expensive, it's more expensive than the day-ahead. But what is this process of the electricity markets? How we deal with these electricity markets? Well, basically, it's a very traditional or conventional process of the market. There are different participants or players in the market. They all offer their bids. Market operator or system operator clear the markets and gives everybody its own share, how much the generations unit needs to produce the electricity and how much demand can consume the electricity. So everything is okay with this process. Everything is fine. That's what what the people are doing for like last 50 years. But what happens if one of these participants is some suspicious participant, someone who wants to take advantage of the systems? Then these participants can manipulate the outcome of the market, the market prices, by injecting the false data into the system and take advantage of the market clearing process. If I want to show the cyber attacks can happen anywhere into the system, and there are a lot of different versions of these cyber attacks into the system. Basically, we are talking about the intrusion in this dissertation and in this project. We talk about the intrusion points and false data injection types of the attacks, but there are more types of attack, like denial of the service, like the time synchronization attacks, like man-in-the-middle attacks, and well, FDI or false data injections attacks are the one that we are focusing in this presentation. So what do I mean by false data injection attacks? Well, basically, if I am an attacker and if I want to manipulate the system states, I'm going to inject some false data into the measurement system. And then this measurement system can be remote terminal units or phasor measurement units. They can be different types of the measurements around the system. But I'm going to follow two main rules, or two main goals, I can say. Well, the monetary attack or monetary goals that I want to take advantage by attacking, by injecting the false data, or I'm just attacking in order to do some terroristic attacks, like the Stuxnet virus happened back in 2015 in Iran. That's, well, it was like mostly like disruptive attacks. There wasn't any monetary goal behind it. But no matter that types of the attacks are, still we need to focus on how we can detect them. In general, I can say there are I can categorize different types of the false data attacks into different sources, or based on different sources, like hardware attacks, that the cyber attacker has the physical access to intelligence devices into substations, where most of these cyber false data attacks happens in this category, because the smart grids, as I mentioned, they are smart, so we don't need to have personnel on the site. We don't need to have too much, humanized work. So that's happens that, well, there is no one to protect your substation, then someone can jump into the substation or can sneak into the substation and change these physical devices. Electromagnetic interference also is another way of this physical cyber attack, which basically, because the in the field, in the smart grids fields, many of the communications are based on the electromagnetic communication, like Zigbees, Wi-Fi, or different frequency range of the communication and the measurements. So the attacker can do the electromagnetic interference attack. Firmware attacks, software attacks, and communication attacks are another versions or another format of false data injection attacks, which can happen based on the resource that the attacker has, and the ability of the attacker has, and also this security of the system. Generally, the other types of the cyber attacks, like firmware attacks and software attacks, are needed someone who has has the access inside the smart grids, and need somehow like a man inside attack. With this brief introduction, I'm going to talk about the different contributions that I had during my PhD. The first contribution that I'm going to talk is about detecting the cyber attacks using the optimization approach. So what is the problem statement here? I can say that if I am an attacker, I want to know what are the intrusion points. Is it here? Is it here? 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 Well, if I'm an attacker, I want to know that what is the best possible points to manipulate. That's how I'm going to look at this problem. And then when I find these intrusion points. I'm going to dig a little bit.
Can you make it in the full screen? Because our pictures are big. Your whole PowerPoint is very small. Can you make it as a big, like a expand, or that is the only size you can put it? Because it looks your picture is bigger than the screen itself. That the PowerPoint thing I see. This is a PDF or a PowerPoint?
It's a PowerPoint. I think you need to.
But can you put it in the presentation mode?
It's already in presentation mode.
Oh, is it? Why it is so small? Yeah.
I think you should click this. This PowerPoint, and then it is a swap. Currently, they show this kind of major. Yeah, I think. I think you should click the PowerPoint window to the top of the right. It's called swap shared screen with a video, and then people will see it. You will see the much bigger one.
It is I have to do it, or he has to do?
You have to do it. You know that on this screen, on the top, on the small one, on the top right, there's a button. It's called.
Yeah,
share.
that's what I did. That's what I because in all the presentations I put it in the speaker view also.
Yeah, let me.
Even then, it looks very small. I don't know why. Is that?
Yeah, let me show you for this one.
Yeah, ours is big, by the way.
Is it?
Yeah, it's big. It's just.
Because I put it in the full screen mode.
Yeah, and let me show. I just send you a kind of screenshot. Yeah.
Oh.
Can you see this? I just sent you a message.
Message on my phone.
Yeah, on your phone, and then you can see this. You see the swap shared screen with video.
Yeah, I saw that one, but
then you just click it, and then you just swap, and.
Yeah, but that is still smaller, because when I see some other presentations, it occupies my whole screen. That's why I was wondering. This is only 1/4 of my screen. It's okay. I can manage.
Maybe you could email your PowerPoint presentation.
Yes.
No, it's okay. It's all right. Don't worry. I can still see it. I was wondering why it is like this, because it never happened. Because all the other presentations I see full. When my students present, it's all full screen, and I see the small pictures of them. Here I see big pictures of all of you, but small of the reverse.
On the top, I see
double click.
On the top, I see view options. Maybe try to make it bigger.
View options.
Doctor, can you double click on
request reverse?
Yeah, feed to window maybe.
Yeah, exactly. Maybe that might help.
Yeah, I made it 100% original size.
Okay, now it's work. Yeah.
Okay. Now the PowerPoint is only off. Yeah, maybe I should reduce it. All right, I will make it 150%. Yeah, now it is fine. Okay.
Thank you.
I made it 150%.
Thank you.
Okay. All right, thank you.
Thank you. So and the other parameter, or the other factor that I care is how would be the values of these false data. So for this work, we presented a bi-level attack model, which basically in the upper level, the attacker consider its objective function or profit by participating in electricity market, and also the fact that the attacker wants to remain undetected. And in the lower level, the attacker needs to consider the power flow constraints, or basically the day-ahead and real-time market constraints in his decision-making. And also, we consider that the attacker participate in both day-ahead and the real-time market. So the intra-correlation between these two markets is also important for the cyber attacker. And finally, we solved the problem using the MPEG mathematical programming with equality constraints in this work. So what are the day-ahead electricity markets? Day-ahead electricity markets, in a simple or linear form of themselves, they are nothing but a simple linear programming. This system operator wants to minimize the system cost, and also it wants to consider the fact that the loads and generation needs to stay in balance together. There are some line limits that the system operator needs to consider, and also, well, each generation units and each load units, they have their own limits, and the phase angle also must remain in a predefined period range. So if we consider the right-hand side figure as a graph of the system, what happens after running these equations is that this system operator would find out theta and lambda as system states and the output of this optimization problem. So which lambda is the day-ahead price and phase angle are theta. The same thing goes for the real-time electricity market. So again, we have the cost of the real-time electricity market. We need to make sure that the load and generation increments are remaining balanced. Also, we have the limits of each increment, and well, the line limit increments as well. We need to make sure that we are not going to make the system worse in terms of the congestion. So again, in these electricity markets, what happens is that the market operator finds out the real-time prices, the amount of the increment in generation or demand. So from the attacker's perspective, yeah, if I'm an attacker, I need to consider both of these markets, and also I need to consider that system operator wants to minimize the cost of the operation, and also system operator wants to consider the constraints in the day-ahead market, as well as the day-ahead, as well as the real-time constraints that it deals with in the real-time situation, and also real-time costs. So I need to consider these problems. And in the upper level, I have the question to ask that what measurements should I manipulate? Should I manipulate measurement number M? In this case, I'm going to use a binary decision-making variable. If I'm going to manipulate that measurement, I'm going to consider it as I'm adding some delta ZM2 to the original equation, and if not, well, that would be itself by itself. So, electricity markets participant in general versus the attacker. There is only these two red boxed constraints that you see here. The cyber attacker needs to consider that if it's inject too much of false information, then it's going to be detected by the system operator, and also needs to consider that there are some limits in terms of the resources. Well, if I am a cyber attacker, I cannot manipulate whatever the measurements or what in terms of the number I can manipulate. Well, and also the rest of these equations are the same for any other participants in the electricity market. The day-ahead and the RT constraints, and also power consumption in day-ahead and RT market. Now, how we solve the problem? Well, we're going to use some duality and some Lagrangian multipliers of the day-ahead optimization problem and the real-time optimization problem. And when we're going to, then we're going to form the Lagrangian problem of day-ahead and the real-time market together. We're using the G and G prime and also the Lagrangian multipliers of the day-ahead and the real-time market. So the problem formulation becomes like, we have the profit of the cyber attacker. Cyber attacker needs to consider the duality problems and duality constraints and also Lagrangian constraints as the day-ahead and RT market effects in the decision making. And also the attacker, as I mentioned, needs to consider whether it wants to attack to the system, whether it wants to attack to the system, to the measurement number M or not. So the lower part is for the decision variables of the attacker. So by applying the model and using the MPEG, if we consider the figure as a base case, you see that we have the day-ahead and the RT prices. The electricity prices would change after the attack based on different scenarios for different boss numbers. So considering the amount of the resource that the attacker has, the attacker can influence on the real-time market, real-time prices, and the day-ahead prices. And also, at the attacker, we were interested in the possible intrusion location in the system. So based on different resources or different number of possibility of possible attacks, we have prioritized the table, and we see that the measurement on line number 4 are the best for the attacker. And if the attacker has the ability to choose just one measurement, then probably is going to be line number 4. And if I am a system operator, then I'm going to reinforce the measurement on line number 4 to just make the attack profits less, and gives the incentives of the attack to the cyber attacker less and less. The problem that we've solved is very good, and we detected the possible cyber attacks. But there is a but. I can say that while solving the problem for the cyber attacker gives us direct solution for possible weak points, so we can directly solve the cyber attack problem. But if we want to consider the attacker's perspective, then we can say that the attacker needs to estimate many parameters, like network parameters, other participant proposed offer, and also the residual constraint of the optimization problem is hard to solve. So the cyber attacker needs to estimate a lot of those parameters. And well, it's not impossible, but the attacker needs to have someone into the system, so can take advantage of the system information. So what are the possible solutions that we can model a more realistic version of the attacks, and then we can detect it without using any assumption from the attacker's side? Well, I can say that we can use that using the indirect approaches, data-driven approaches. And well, when it comes to data-driven approaches, I can say that deep learning methods are the best in terms of using the data and then come up with some solution. So that gave us the idea.
Yeah, I think you need to speed up a little bit.
Sure.
Already 35 minutes. Yeah.
Sure. So no, there were. Okay, sorry. So let's talk about the contribution number 2, and that's what made us to reach the contribution number 2. Well, basically, in our second work, we considered that there would be some zero-sum game problem. There are 2 parties in our problem: cyber attacker and the system defender. Cyber attacker wants to detect the attacks, and the attacker wants to be anonymous. And if you consider these figure on the right bottom of this slide, you see that there are attackers in the system, and these attackers or attacker sends the false data into the SCADA system. And if this attack signal passed the detection mechanism, then the attacker would have influence. And on the other side, we have this system operator or electricity market operator who wants to detect the attacks. So the idea of the zero-sum game is very realistic, and also we can use a new or a better data-driven model using the generative adversarial networks. So you see that on the top side there is a discriminator, and we have the generator. So how we can apply this generative adversarial network infrastructure or model to our problem? Well, it's pretty the same as you see in the structure of the GAN. We see the generator network, which plays the rules of the cyber attacker, and we have the discriminator network, which plays the role of the system defender. And these 2 networks are going to fight against each other, and each one wants to defeat the other ones. So a little bit talking about the mathematical point of the problem, we can say that if we have 4 different types of the distribution distribution data that the generator or cyber attacker generates, the noise that is input of the cyber attacker, the discriminative distribution or distribution of the discriminator network over the data, and the real data itself. So as I mentioned, the problem is zero-sum or min-max optimization problem. And well, basically each party tries to deceive the other part. If discriminator network, or D, tries to maximize its objective, and also generator network tries to maximize its objectives, or better to say, minimize the discriminator objective. So this gives us a very good intuition about how we can formulate our problem. Basically, I can say that if I am a cyber attacker, and if I have the access to, even though if I don't have access to anything in the system, by just looking at the electricity prices, I just say that I want to generate the signals that cause the highest possible of the electricity prices, considering that the day-ahead prices are constant. So I can say that I'm going to using this infrastructure on the right-hand side by considering that I want to generate the signals that cause the electricity prices, real-time electricity prices, getting higher and higher. Well, this infrastructure is good enough, but there is a point. Sorry, there is a problem regarding this infrastructure, that the cyber attacker doesn't have the ability or control over the generated signals. Let's give you an example in this regard. As you see, there are, I consider the difference between real-time demand and the day-ahead demand as an X, and the real-time price and day-ahead price as an Y. And as you see, I can divide this signal into two different distributions. As you see, regular distribution or regular demand, and the desired demand. Desired demands are those demands that cause the electricity prices goes higher and higher, and the regular demands can cause high or low electricity prices. So I'm going to mimic this distribution with a new infrastructure of the GAN, or new structure of the GAN, which basically we have the discriminator network and the generator network here, and an autoencoder in the middle. So the autoencoder objective function is to generate the desired signals, or the desired distribution that the attacker wants. And the discriminator network objective function is to detect those signals. Also, the generator networks wants to generate just the normal and regular the signals. But if we combine the output of the generator and the output of the autoencoder using some alpha and beta here, alpha and beta, then we give the cyber attacker the ability to control the generated signals. But how is this possible? Let's, well, before going to the results and show how the result is, let's say that the training phase of these three networks needs to be in two different separate loops. Inner loops are for the autoencoder and the discriminator, and the outer loops are for generators. So the generator loss, in terms of the training results, the generator loss are depicted here. But the one that is very interesting for me is that the loss of our presented model, the three-layer model, is higher than the regular GAN, which means that we have created a cyber attacker that can fool the system discriminator better than just a normal GAN. And as you see, when we apply our new generator or new cyber attacker structure to the simple discriminator GAN and the discriminator network that we have created, our network outperforms the regular discriminator networks. So if I want to show the PCA analysis of the output of both these three networks, I can say that by changing the alpha and beta, the distribution of the data would change. And as you see, when the alpha is higher, so we are interested in creating more desired types of the signals. And as you see, the output of the cyber attacker, the changes to the forms of the desired data. And when the alpha is less than beta, which it means that the attacker is going to generate more realistic signals, or more signals, or signals that are not creating a lot of profit for the cyber attackers. So we can say that by changing this alpha and beta, we are able to generate a very huge distribution of possible fake signals, and our discriminator network, which is our aim to be trained, which is going to learn more from different distribution of the data. Now, after this, these two works that we were working on the detection of this.
I have a question.
Sure, doctor.
So in terms of, you change alpha, beta, obviously during simulation, right?
Yes.
So in real life, what is the meaning of that? Let's say if you are an operator trying to see if there is, let's say, intrusion and that kind of.
Yes, thank you for asking the question. So in real life means that if I am a system operator, I'm going to consider all possibilities of the combination of these two distributions that I showed here. If I am a, you see these two distributions here. These two distributions are inside the data, and the cyber attacker can change these two distributions into different formats. So if I am a system detector, I'm going to consider the chance of these signals, how these signals or this distribution can change, and then I'm going to train a deep network based on these different distributions, and I'm going to find out finally that here, if the signals coming from the measurements, if they are more like these types of the signals, when I can say that these types of the signals are suspicious for me. And if the signals are like these forms, then I can say that, well, there wouldn't be any major, any major problem with the signals that I have. So basically, I am going to train with different alpha and beta, and then I'm going to investigate these PCA analysis and see whether the signals are suspicious or not.
Thanks, go ahead.
Sure. So the last work or the last contribution is out of the detecting area. So we're done with the detection area, and we're going to see that, okay, now let's say that by considering all of these fancy methods that you're giving us, Saeed, cyber attackers somehow intrude into the system. Okay, now what should we do and how we deal with the problem? That's another interesting question. That's why I'm going to talk about it here. Let's say that cyber attacker attacks in here. Okay, so the system operator is in charge of the keep frequency and keep the voltage in a very good level of operation. So well, that's nice. So okay, I'm considering right now that I cannot do anything with the cyber attacker, and cyber attacker somehow intrude into the system. Now I have couple of choices here. Well, the cyber attacker attacks here, I'm going to redispatch the generations in order to mitigate the effect of the cyber attack, which basically, as you see, these are these red arrows, which shows that this network is kind of congested and I need to redispatch the generators. Or I can decrease the load. I can just cut some loads in order to make the network less stressed or less under pressure. Or I can do some system reconfiguration, as you see here. Well, in this work, we were focusing on redispatching of the generators. However, if I'm going to suggest the load shedding and system reconfiguration in the future work as well. Now that you are familiar with what is the problem, what is the source of the problem, I'm going to talk about the objective of the system defender and the single stage and multi-stage mitigation methods. Let's say that the cyber attacker attacks to the system and cause the system goes under pressure. As you see here, the system is heavily loaded. Now, as a system operator, I have two main goals. I want to maximize the free capacity of the system. Let's say that here the free capacity is 3 arrows. And I also want to consider the system constraints. I also want to make the system stay, keeps its balance, keeps the balance between load and generation. So as you see, the free capacity is like 3 here, 3 arrows. Now I'm considering to shed some loads. And then as you see, the capacity of the system increases and the system goes out of the pressure. That is single stage game. Basically, the attacker attacks and the cyber and the system defender is going to take some countermeasurement. For a multi-stage attack, again, the cyber attacker attacks here as we had it previously, but the system defender, before taking any action, is going to consider possible attack scenarios in the future. So if I'm going to take some action, I'm going to consider the fact that the cyber attacker can attack to the system again. The way that we're going to model the problem is going to be explained in the future slides. But now, okay, I consider the possible next attack solutions, and I again come up with a load shedding solution. Now, if I calculate the capacity of the system, the capacity has increased. For the second stage, as I already predicted, the attacker attacks here. Again, the system goes under pressure, and I'm losing the capacity of the system. Now I'm going to consider possible attack scenarios, whether the next attack would be here or not. So based on this prediction, I'm going to suggest the system reconfiguration. And where by this system reconfiguration, I increased the free capacity from 0 to 2. Now let's talk about the mathematical formulation of the problem. Well, the problem can be very more complex problem than what I'm going to show. But let's consider that the objective function of the system defender is to increase the system capacity after the cyber attacker attacks. And well, the system capacity limit would be like this. Line flow balance, we have it here. And as you see, the VI and theta are voltage magnitude and angle here. And the nodal power balance, we have to make sure that the general active and reactive power generations and the loads are remain balanced. We have the generation limits, ramp limits of the generation, voltage limits of the generation, and the line limits. We have to make sure that this line limit also wouldn't go beyond the system capacity. And if we have some overcurrent limits in the system or overcurrent relays, well, we need to consider that protection device as well. So what the people are doing right now? Well, in reality, the people are using a lot of those non-convex optimization methods, or I can say Bender's decomposition, alternative direction method of the multipliers, which they are very powerful tools, but they have their own drawbacks as well. Well, as I can say right now, when the problem happens, when something happens, you have to run all the aforementioned equations that I showed to you, and you have to run it each time. And also, the computation burden of these equations grows with the size of the network. And since we have a smart grids expanding, when the problem grows, expand as well. We don't have any memory in learning when we're using these optimization methods. Each time we have to run it. And well, in terms of the distributed learning, so far, these packages, optimization packages or infrastructures, they haven't shown the performance of the deep networks that we already experienced it before. So they don't have the ability to perform good on the GPUs for now. And well, if you add more uncertainty to problem, then you have to consider, you have to solve the optimization problem again for any of those uncertainties or scenarios. So what do you suggest, or what I suggest? Well, I say that I will use the reinforcement learning problem, which basically it considers the system capacity as the immediate reward of the reinforcement learning agent. Then we're going to consider action sets for the reinforcement learning agent, which is nothing but the voltage of the generators and the active power of the generators. We have some states regarding our power system, the amount of the voltage after we take action, the amount of the phase angle, power, active and reactive power generation, and also active and power flow of the system. And well, we have the load flow equations to solve, which is not a big deal in many cases, and they are very fast to converge. So the idea, as you see, is here that in T is equal to 1, the cyber attacker attacks to the system. We calculate the system states or system information, and we feed those information into our reinforcement learning agent, and our reinforcement learning agent is going to tell us to increase the active power of this generator. So this is the idea of the single stage game using the reinforcement learning. But what happens when we have multi-stage game? Well, we need to model the next attack's location based on the current attack location. And as I can say that these problems cause a lot of uncertainty here. So if the cyber attacker attacks in here, then next step can be here, here, or anywhere else. So I suggested using the Hamiltonian Markov chain, or better to say Markovian chain problem, which basically you decide the next opponent moves based on the current opponent situation. So this Hamiltonian Markov chain use a Bayesian equation, and as you see, in order to obtain the posterior distribution of the attack's location, I need to consider the current attack distribution or current attack location and the likelihood of the possible attack location regarding the current attack. And well, the same thing goes for the cyber attacker. So if I am a cyber attacker, again, in order to find the optimal attack location, I need to consider my current attack and the likelihood of the system states based on my current attack. And in this problem, I've considered from the attacker perspective, I consider the normal distribution for both system states and the system operator actions. So how do we obtain the posterior? We use the Hamiltonian Markov chain. Hamiltonian Markov chain follows the Hamiltonian dynamics. Hamiltonian dynamics says that the energy of any system is equal to kinetic energy and the potential energy. We have proved in our thesis that this would be equals to minus log the disjoint distribution of the attack and some auxiliary variable. We know it as a momentum here. After some manipulation, we found out that the UX, or the potential energy of the attack location, would be minus log P probability of the attack. And the momentum will follow the likelihood distribution of the attack location. The Hamiltonian dynamics would be solved by just simple derivatives. So we derive the attack location that we are looking for, and the momentum that is just an auxiliary variable regarding to the energy of the system. And we reach to famous leapfrog equations that is nothing but just an updating rule based on the derivatives that we obtained earlier. So if I want to make it all briefly here, I can say that the Hamiltonian dynamics follow a simple updating rules, which basically says that we consider a prior distribution for our attacks location as we already have it. Then we have a momentum variable, which as I mentioned, is nothing but just auxiliary distribution. Then we're going to execute leapfrog method, as I showed the equations previously, and we're going to obtain a new x and a new m. Now I'm going to solve to just calculate an accuracy rate or accuracy metric. And if this accuracy metric is greater than some random variable, I'm going to consider the new attack locations as the possible attack location that might happen, considering all those prior mentioned, above mentioned situation. Now let's embed it into our problem, and let's model it based on our problem. Well, I can say that in a multi-stage game with reinforcement learning, the cyber attacker is going to specify first set of possible elements, and then it's going to run Hamiltonian Markov chain Monte Carlo. And then, as you see, is running here, and then it's going to find the distribution of any of these attacks locations. And then by resampling and applying a softmax, the cyber attacker is going to attack to these elements in the network, in future. So the same thing happens for the defenders as well. System defender is going to apply the cyber attacker, current cyber attack locations, then it's going to run Hamiltonian Monte Carlo Markov chain, is going to find out the possible scenarios of the attack in the future, and then it's going to find out the transition probabilities of the reinforcement learning environment. Then it's going to run this reinforcement learning environment, but it would consider that the future possible attacks would be here, and it's going to be reflected in this decision-making problem. Then the system defender is going to obtain action and the Q value or possible expected profits of taking this action, apply this action and update the environment and wait for the next possible attacks that may happen in the system. Now, I've used a DDPG or deep deterministic policy gradient structure in order to train my reinforcement learning agent, which basically this DDPG is nothing but a deep network infrastructure that consists of two different networks, a critic network, as you see the upper side, and the target network in the lower side. The critic network is going to see the current state of the system and takes the action of this actor network, and then it's going to tell the actor network that have you take a good decision or bad decision. So it's going to tell me what is the Q value of the system based on the actor input. And well, the optimal, this network is the original critic network. And I have, as I mentioned, I have another target critic network, which is going to tell me the optimal Q value for taking action AT and ST, which we have it here as a famous Bellman equation. So by just calculating this optimal value, mean square of this optimal value and the value we obtained here, we're going to find out the loss of our network. The same thing or the same rule happens for the actor network. The actor network is going to take the actions that maximize this Q value. So the objective of the actor network is to maximize the Q value. And the problem would be a maximization. And while we have another target actor network here, which basically does nothing but just waits and see whether the taken actions by the actor network is good enough or not. If it's good enough, then it would take that action. Here are the simulation results based on the single stage game. And as you see, the immediate reward is going to increase after some iteration. And we have the critic loss and the actor loss for our actor and critic networks. But let's give you some attack scenario over some case study. Let's say that, well, I've considered this 24 bus IEEE system, and then the attacker attacks in here. Well, I apply this attack to my reinforcement learning agent, and it's going to tell me that, okay, increase these generators in order to remove the overloads happens here, here, and here in my network. And well, I've added more attack scenarios here, and as you see, after reinforcement learning take actions, the current overload when the attacker attacks the system and after taking the action would be 0. For the multi-stage game, we are interested to obtain the prior and posterior distribution of our actions. So based on the posterior distribution of the cyber attacker and the resampling from the single stage reinforcement learning agent, we're going to obtain the posterior distribution of our generation units. And as you see, for some cases like generation 1, the generator would be more conservative, while for the generator 2 would be more risky and is going to accept more risk. And for the generator number 3, it would be somehow risky, somehow conservative. Finally, I can...
Saeed, I have a question.
Sure.
In your simulations, are you considering only one attacker all the time?
One cyber attacker, but different locations.
What happens if you have multiple attackers?
Still the problem... Still, the problem would be, I mean, the procedure would be the same, but we need to consider 2 possible posterior, and each time we need to simulate 2 posterior distribution for cyber attacker.
Okay.
Yeah, with different distribution or with the same distribution. It depends on what real information that we have from the previous attack distributions. Now,
also you need to have a kind of a mechanism to estimate how many bad guys there.
Yes.
Yeah, but anyway, that is another story. You don't need to concentrate on that. Yeah, please.
Yes. So for the future work, I can say that so far we have used a lot of generative models that made us more model better to make a decision. But we have to increase the detection network sensitivity to fake signals by the system attacker by adding some style transfer learning, some variational autoencoder into the GANs, and some Bayesian methods or Bayesian approaches in order to create more powerful or better cyber attackers. Then if you create a better cyber attacker, as I showed you, a better cyber attacker would cause a better system discriminator for you. And then you have seen more distribution of the possible fake signals. In terms of the cyber attack mitigations, well, as I mentioned here I consider just the generation of the redispatching of the generation. The problem can goes far beyond of the redispatching, can goes like system self-healing with the load cutting or load shedding, load management, or also system changing the system configuration. And also, if you want to apply the model on a bigger system, you need to definitely change the structure of the system to some sequencing models in order to add more memory to your reinforcement learning agent, which would cause a more powerful reinforcement learning agent. So at the end, I can say that the conclusions can be briefly mentioned here, like we've used optimization methods to detect the weak points and the possible false data values. We used machine learning in order to detect the cyber attacks based on the zero-sum game and based on the GAN. And also we have created and we have used an autoencoder in order to create a better cyber attacker or more distribution of the data. And also we use the reinforcement learning, and then we combined it with the Hamiltonian Monte Carlo Markov chain in order to model the single stage and the multi-stage attack mitigations. Here are the list of my publications that I had so far. Some of them are still under review, some of them are ready to publish. And thank you all for giving me the opportunity and the chance to present my work for you, and I'm really sorry for inconvenience happened earlier at the beginning of this meeting.
Okay, I think you can start.